Hey everyone, and welcome back to LearningHub. If you've ever tried to build an AI that understands language, you probably run headfirst into the biggest and hairiest problem in deep learning, that is, the gradient problem. Remember those frustrating recurrent neural networks? They were slow, they couldn't process data in parallel, and worst of all, they suffered from the vanishing gradient, meaning they had the memory of a goldfish when dealing with long sentences. But in 2017, everything changed. Researchers threw out the old playbook and introduced a revolutionary idea, that is, the transformer architecture. And the core principle behind it, the paper, attention is all you need. So before the transformer, models like RNNs and LSTMs process data sequentially, struggling with long-term memory and parallelism. The transformer ignored that sequential processing, relying instead entirely on a mechanism called self-attention to capture relationships within the data, no matter how far apart the words are. This makes the transformer significantly faster and good at understanding context across huge amount of text. The two pillars behind transformers, encoder and decoder. The original transformer is built using a classic encoder decoder structure made for sequence to sequence tasks like language translation. Example, translating English language to French. We'll talk about the encoder part first. This is the understanding component. It takes the entire input sequence like the English sentence and transforms it into a rich contextual representation. Think of the encoder as reading and fully comprehending the text or input text, producing a powerful summary that retains the meaning of every word in the context. Next is the decoder part. This is the generation component. It takes the encoder input or the encoder's output, that is the summary, and uses it to generate the final output sequence, like the French translation, one word at a time. The decoder is mainly focused for translating the encoded understanding into a readable, relevant output sequence. The encoder block is the part of the transformer that takes care of the input sequence and converts it into a rich contextual representation. And the very first step in this process is the input embedding, which is crucial for preparing the raw text for the neural network. So the figure you see here illustrates how the input sequence is processed before it even enters the encoder's main layer. So first of all, input embedding process. So the input to the transformer is a sequence of token, that is words or subwords. The encoder transforms this input into two main steps. The first is input word embedding. Deep models can't rely directly on deep model deep learning model cannot directly process text. They need numbers. Word embeddings convert each discrete word into a continuous vector of real numbers. As shown in your figure here, for an input sequence of length 6, each word is mapped to a vector with an embedding dimension of 512. And then we get that the input sentence will be transformed from sequence of words into a sequence of matrix of size 6 into 512. This matrix represents the initial meaning of the words. So as we talked about, the transformer architecture processes all the words in a sequence simultaneously. While this parallelism makes it incredibly efficient, it also means the model inherently loses the information of about the order of words in a sentence. Without knowing if the dog bites man or man bites dog, the meaning is lost. This is where positional encoding comes into play. It's the ingenious mechanism that injects crucial sequential information into the model. So why do we need positional encoding? The need for positional encoding stems from three key requirements. First, Each word should carry some information about its place in the sentence. That is, the model needs to know where a word sits relative to others to understand grammar, syntax, and overall meaning. The second, we want model to treat words that appear close to each other as closer and far as far. That means the encoding should reflect proximity. Words next to each other should have a similar positional encodings, while words at opposite ends of a long sentence should have completely variable type of encodings. Third, we want positional encoding to represent a pattern that can be learned by the model. So the specific numerical pattern used for positional encoding isn't just random. It is made to be unique for each position and to allow the model to easily deduce relative placements. Example, this word is two positions from that word. This is typically achieved using sine and cosine functions of different frequencies. So how does the data flow from original sentence to encoder input? We'll trace the journey of the sentence, your cat is a lovely cat, through the initial stages of the transformer encoder as shown in the figure. First of all, we start with this particular original sentence here. Each word in this sentence is considered a token. Then each token or word from the original sentence is first converted into a numerical representation called an embedding. This is where the word's meaning is captured in a dense vector. So at this stage, each vector contains the semantic meaning of the word, but still no information about its placement in the sentence. So the two words cat would have identical embeddings here if the model learned the same meaning for both, even though they are at various places. So for each placements in the sentence, maybe for position 1, position 2, position 3, and so on, a unique encoding vector, that is called the positional encoding vector of size 512 is generated. 512 in the, with reference to the example taken here. So these are the vertical bars that we see here. The positional encoding is only computed once, and then they're reused for every sentence during both training and inference. It is not something the network learns in the same way it learns word embeddings. It is a fixed pattern added to the input. So each of these positional vectors is unique, ensuring that even if two words are identical, like the two cats that you see here, the overall input to the model will be variable because of their positional encodings that are completely different. Then the magic happens here. The positional encoding vector for each placement is added to or is added element wise to its corresponding word embedding vector. That is why you see the plus sign between the embeddings as well as the encoding vectors here. The resulting vector for each row or for each word is now a blend of its semantic meaning and its sequential position. So the vector that you see here, or the final set of vectors, one for each word, now becomes the encoder input. Each of these vectors is still of size 512, but now it carries complete information, the inherent meaning of the word plus its specific location within the sentence. The enriched input is then fed into the subsequent layer of transformer encoder for deeper contextual processing. Now we'll see how this positional encoding is computed, and then we consider the sinusoidal approach that the paper took. In the paper, attention is all you need. So the magic of positional encoding lies in a specific mathematical formula that assigns a unique fixed vector to each position in a sequence. This isn't learned by the model, it's a pattern or a fixed pattern injected into the input. The formulas for computing the elements of the position encoding vectors are shown here. We'll break it down. So this particular term here, or POS, is the actual position of the word in the sequence, starting from 0, 1, 2, and so on. The value that you see here, I, refers to the dimension within the embedding vector, and this ranges from 0 to d underscore model minus 1, which means, so d underscore model is 512 here, so it goes up to 511. We use both 2i and 2i plus 1, so I goes from 0 up to d underscore model divided by 2 minus 1. Now d underscore model, this is the embedding dimension. We've taken the embedding dimension to be 512 here, and then you also see this particular constant here. This is a fixed scaling factor chosen empirically. Now if you look at the denominator part, this part creates different wavelengths for sine and cosine waves. You can see this in the figure 2. As I increases, meaning we look at the higher dimension within the embedding vector, the denominator gets larger, making the wavelength of the sine or cosine function longer. Conversely, for smaller I or lower dimension, the wavelength is shorter. So the same PE value or the encoding vector is used for the same position regardless of the sentence. Suppose we consider two sentences here. The dog ran and a cat jumped. So the vector value for the first word in the sentence the dog ran or a cat jumped will be the same. This ensures consistency and allows the model to generalize placements across different inputs. Now, why sine and cosine functions? The choice of sine and cosine functions isn't arbitrary. It's brilliantly designed to provide unique and easily interpretable position information. Every placement or position will have a unique sinusoidal positional vector. This is because at least one dimension of the vector will have a unique sine cosine value. The second figure that you see here, or the heat map, visually demonstrates this. Each horizontal line represents a position in the sequence. We have considered up to 2000 words here, and the color changes along the line indicate the value of the 512 dimensions, that is the depth. You can see a fixed undulating pattern for each position. A critical property of sine and cosine function is that a linear transformation can represent any kind of phase shift. That means the positional encoding of a word at placements POS plus K will take the word dog maybe at position 1 can be expressed as a linear function of the encoding of a word at placement 0. So this property is incredibly powerful. It allows the transformer model to easily learn and generalize relative placements. It doesn't need to learn an absolute placement for every single word. Instead, it can learn that the two words or the word two placements after X has a specific relationship to X. This allows the attention mechanism to efficiently figure out how related words are based on their proximity. And since these are functions, they can theoretically generate position encoding for any sequence length, even though longer than the ones encountered during training. This makes the model more robust and flexible. So in essence, the sinusoidal position encodings provide a way to inject order information into a parallel structure or parallel architecture without losing the benefits of parallel processing. They ensure that the transformer knows where each piece of information stands relative to others, which is fundamental for understanding the complex structure of human language. Now we move on to the self-attention. The self-attention is the revolutionary mechanism at the heart of the transformer architecture. Actually, we needed to talk about the multi-headed attention here, but first we'll discuss the self-attention after we have completed this particular part here. Okay, so the self-attention allows the model to process sequences in parallel and understand the relationship between different words in a sentence, no matter how far apart they are. The fundamental idea is simple yet very powerful. Self-attention allows the model to relate words to each other. Imagine reading a sentence and pausing at the word, asking yourself which other words in this sentence are most relevant to this word. Self-attention does precisely that, but computationally and for every single word simultaneously. And the core idea behind self-attention are the query, key, and value. So the self-attention mechanism works by computing three matrices from the input. The first one is the query or Q. Think of this as the question or what a particular word is looking for. The second one is the key or K. These are like labels or indexes for all the words in the sequence. Each word offers its key to be matched against the query. And the third is the value. These are the actual content or information associated with each other that will be returned if the key matches a query well. And the goal is to calculate how much attention each word in the sequence should pay to every other word, including itself, to complete or to compute its new context-rich representation. We'll break down the formula that we see here and the matrix operations. So basically, attention matrix is created using this particular formula here. We'll consider a few values. In our case, sequence length n, we're considering it as 6. We take 6 words. Embedding dimension d underscore model, we're considering it as 512. And the key dimension d underscore k, we're just talking about a single head. So basically d underscore model will consider the same as d underscore k, which will be 512. Now we'll trace the steps. Initially, the input to the attention mechanism is the sequence of 6 words, each represented by a 512 dimensional vector. And where does this vector come from? This particular vector comes from here, which is the encoder input of size 6, 512. So instead of directly using this input matrix as Q, K, and V, the transformer actually projects this input into 3 separate matrices Q, K, and V using learn to weight matrices. However, for simplicity, in our case, we've shown that Q, K, and V are essentially derived from the input sentence itself, each also having dimension 6, 512. Then we calculate the similarity. So we take the query matrix that has dimension 6, 512. We multiply it by the transpose of the key matrix, which has dimension 512, 6. The result is a matrix of shape 6, 6. After applying the softmax, this matrix shows us or represents the raw attention scores or compatibility between each words in our 6-word sequence. So the raw attention scores are also divided by the square root of d underscore k, which is 512. The scaling factor stabilizes the gradients during training, preventing very large values from dominating. Also, we apply the softmax function to each row of the scaled 6 by 6 matrix. Softmax turns these raw scores into attention weights that sum up for 1 for each row. This means that for each word or for each query, you get the probability showing how much attention it should pay to every other word or the key. So these are the weights of importance. Finally, what we do is we multiply this 6 by 6 matrix of attention weights representing who pays attention to whom by the value matrix, which has dimension 6, 512. The result is the attention output matrix, also of shape 6, 512. This is shown in the diagram as the final attention matrix here. The self-attention as performed in the transformer encoder is defined by several different properties and yields a crucial output, the attention weight matrix. Now we'll talk about the self-attention properties here. First, self-attention is permutation invariant. The raw self-attention operation, the calculation of QK transpose followed by the softmax, does not naturally encode order. If you randomly shuffle the words in the input sentence, the mathematical result of the attention calculation would also remain the same. This is precisely why we absolutely require positional encoding. The positional encoding then adds the sequential information back into the input embeddings. Up until the attention step, the interaction between words have been purely driven by the initial embedding and the positional encoding. Second, self-attention requires no parameter for the core calculation. The core QK transpose operation is itself a parameter-free calculation. It is simply a dot product measuring the similarity between the query and the key vectors. However, the mechanism as a whole does use parameters. The initial linear layers that create the Q, K, and V matrices from the input are learned weight matrices. These learned weight define how the model searches for relationship. And finally, expected high diagonal values. When looking at the resulting attention matrix, an example is shown here. We expect the values along the main diagonal to be the highest. Why? The diagonal represents the attention of the word that pays to itself, meaning the attention the word your pays to your. Since the most relevant information for the word's new contextual representation usually includes its own original meaning, the model typically assigns a high value of weight to its own value. The color grid that you see here shows the actual attention weights for the sentence. Your cat is a lovely cat. Each row represents the attention weights for that particular specific query word, and each column or the values across the rows shows how much attention that query word pays to every key word in the sequence or in the sentence. Now look at the diagonal. Self-attention is high. For most words, the diagonal value is among its highest in its row. So for cat to cat, it is almost 0.229, and from lovely to lovely, it is almost 0.227. Sorry, 0.227. This confirms the expectation that words prioritize their own information. And more interestingly, the model gets to learn relationship here. So the first word or the first cat pays significant attention to the word your and the word is, which is essential for understanding the subject and the verb structure. Similarly, the word is pays high attention to the word a or a here, a, and the second cat as the verb links the subject phrase to the object phrase. But we have a special property in case of decoder, which is masking. So if you don't want some positions to interact, we can simply replace or set their values by minus infinity before applying the softmax, before doing this particular part here. The softmax function works by exponentiating the input. Exponentiating minus infinity results in 0. And by setting an attention score to minus infinity, the softmax operation ensures that resulting attention weight is 0, meaning the model will not learn or use information from that specific interaction. This technique is essential in the transformer decoder during training and generation. When the decoder is generating the teeth word here, it must not look at the words at the position t plus 1, t plus 2, t plus 3 and so on. This is called mask self-attention. And by setting the attention scores for all future positions to minus infinity in the attention matrix, the model is forced to rely only on the words already generated, simulating the real world sequence generation process. Now that we understand the single head attention, let's move on to multi-head attention. So the single self-attention mechanism we previously talked about is powerful, but it's limited. It only provides one way of looking at relationship between words. To make the transformer truly robust, we upgrade this mechanism to multi-head attention. Why multi-head? Imagine a single attention mechanism is like looking at a sentence with just one pair of glass. You might sometimes see the subject-verb relationship, but you might miss the adjective-noun relationship. Now, multi-head attention is like wearing several different pairs of specialized glasses simultaneously. It allows the model to attend to information from different representations of spaces at different positions. One head might focus on identifying synaptic or grammatical relationship, while other might focus on semantic relationship. And by using multi-heads, the model can capture a much richer and more diverse set of dependencies within the sequence. The figure beautifully outlines the 5 main steps required to compose multi-head attention using the key parameters. So first of all, we have a sequence length of 6. The D model, or the size of the embedding vector, is 512. We'll consider H as number of heads, which we'll take as 4 for now. And then now dk or dv. So the dimension of the key, query or value vectors for each individual head is calculated as d underscore model divided by h, which means 512 by 4 is equal to 128. So now, instead of running one attention mechanism on the full 512 dimension input, we first split the work. The input matrix sequence comma D model is linearly projected into 3 full-size matrices: query, key, and value. Each of these matrices is then multiplied by a different learned weights WQ, WK, and WV, all of size D model comma D model. This results in 3 new matrices Q prime, K prime, and V prime, each with dimensions sequence length comma D model. These projections allow each head to focus on a different aspect of the original embedding space. Now, we will split into heads. The Q prime, K prime, and V prime matrices are then split into H separate chunks along the embedding dimension. This creates H sets of Qi, Ki, and Vi matrices, where each set I now has the reduced dimension of sequence length, comma dk. So this is the key to parallelism. Then the H independent single head attention operations are performed simultaneously. For each head I, we compute head I equal to attention Q prime, K prime, and V prime using the scale dot product formula. Each head I output has dimensions sequence length comma dv, which means 6 comma 128. The output from all the heads or from all H individual heads, head 1, head 2, head 3, head 4, are then concatenated or stacked side by side back together. This forms a large intermediate matrix H with the dimension sequence length comma H into dv. Since h into dv equals d underscore model, the concatenated vector or the matrix returns to the original dimension of sequence length comma d model. And finally, the concatenated output matrix H is multiplied by one final learned weight matrix, that is W0, which has dimension D model, comma D model. The final matrix multiplication blends into the information gathered by all the different attention heads into the final, consolidated as multi-headed attention output, which retains the original dimension of sequence length, comma D model. So this multi-head attention output is the new contextually enriched representation of the input sequence, ready to be passed to the next component in the transformer block. This whole mechanism ensures that the model can look at various aspects of the data simultaneously, resulting in vastly improved performance compared to a single attention head or sequential RNNs. Now we move on to the decoders part. While the encoder focuses on understanding an entire input sequence, the decoder is the one that generates an output sequence, typically one token at a time or one word at a time. This generation process introduces a unique constraint. The casual constraint is don't look ahead. We want our model to be causal. It means the output of at a certain position should only depend on the words of the previous positions. Model must not be able to see the future words. So imagine you're writing a sentence. You decide on the first word, then the second based on the first, then the third based on the first two, and so on. You don't know what words you'll write 5 steps from now on when you're deciding on the current word. The decoder must mimic this human generation process. If the decoder will allow to peek at the entire target during training in a translation task, for example, it would essentially be cheating. It would learn to copy rather than generate, and it wouldn't be able to function in a real world scenario where the future words are unknown. Now, to enforce this causal constraint, the decoder uses a special type of self-attention called a masked multi-headed attention. This is the lower multi-head attention block within each decoder layer, highlighted in the architectural diagram that you see here. And how does it work? Just like in the encoder, the decoder self-attention mechanism begins by computing the query and key vectors dot product, which measures the raw attention score between every pair of words in the output sequence generated so far. And here is the attention matrix that we see here. So after the dot product calculation and just before dividing by root under decay and applying softmax, we introduce a mask. This mask is a matrix of zeros and negative infinities. For any position I comma j in the attention score matrix where j is greater than I, meaning word I is trying to look at a future word j, we replace the calculated attention score with minus infinity. So minus infinity here, minus infinity here, minus infinity here, minus infinity here. And then we apply softmax. So when softmax is applied to the row containing these minus infinity values, the exponential of minus infinity is essentially 0. So this enforces the attention weights for all the future positions to become 0. So imagine applying this masking to the attention matrix for your cat is a lovely cat. When the decoder is processing the word your, it can only attend to your itself. When it is processing the word cat, it can attend to your and cat, but not is a lovely cat, and so on. By doing this, the masked multi-head attention ensures that when the decoder computes the representation for the current word, it only utilizes information from the words that have previously been generated in the output sequence. This strictly maintains the causal property required for accurate and sequential language generation. Now we move on to our training. So training the transformer. The training process for the transformer architecture, especially for sequence to sequence tasks like machine translation, is highly efficient because the entire process happens in one time step and it's fully parallelized. We'll use this example, translating the sentence I love you very much from English into Italian, ti amo molto. The first step is to prepare the encoder input. So the English sentence is wrapped with the start of sequence and end of sequence tokens, and then the full sequence is fed to the encoder. The transformer uses the correct target sequence as the input for the decoder during training. This target is also prepared by adding the start of sequence token in the beginning, but the end of sequence token is omitted from the decoder here or the decoder input because the decoder should never see the end token until it predicts it. The sentence is given the output embedding as well as the positional encoding before entering the decoder here. And then we also have the current sequence the model's prediction will be compared against, which is T amo molto. The goal is to teach the model to predict the word T, then predict the word T given start of sequence token, then predict amo given start of sequence and the word T, and so on, giving the full Italian sentence. Unlike recurrent neural networks, which process one word at a time, the transformer processes all words simultaneously. The encoder receives the full English sentence or sequence, calculates all the attention scores and contextual embeddings, and outputs a single encoder output matrix, which is of shape sequence comma D model. This matrix contains the complete context of the English sentence. And then the decoder performs three main attention operations in parallel. First is the masked multi-head attention. It processes the Italian output using masked self-attention to ensure causality. That is, when processing amo, it can only look at the beginning of sequence and the word T. And finally, the encoder-decoder attention. This layer is a bridge. It takes the query and key from the encoder output and the values from the decoder's internal state. This allows the decoder to learn which part of the English sentence are relevant for generating the current Italian word. The final decoder output that we see here is a matrix of size sequence comma D model. Then the decoder output or a contextual embedding is passed through a linear layer. This layer projects the embedding dimension up to the size of the entire vocabulary, resulting in a matrix of size, sequence length, comma vocab size. The output of this particular linear layer is passed through a softmax function, which turns the raw scores into a probability distribution over every word in the vocabulary for every position. The model's prediction or the probability for the sequence is then compared directly against the target output. The difference between the predicted probabilities and the true target is measured using the cross entropy loss function. This single loss value summarizes the errors for all words in the sequence. The error is then backpropagated through the entire transformer, encoder and decoder in a single step to update all the weights and improve the model's performance. This ability to do this entire sequence computation in one parallel step is what makes the transformer so much faster and scalable than the older architectures like RNN. So this brings us to the end of our deep dive into the transformer architecture. We started with the limitations of the old systems like recurrent neural networks. Remember the headaches of the vanishing gradient problem and slow sequential processing. We saw how those issues forced researchers to look for a better way. The transformer delivered that solution by completely throwing out recurrence and embracing attention. We saw how positional encoding cleverly injects order into a parallel system. We demystified self-attention and multi-head attention, which were the core mechanisms that allow the model to see complex relationship between every word simultaneously. And finally, we trace the entire process from preparing the input with the start of sequence and the end of sequence tokens to the efficient parallel training loop that uses masked attention to maintain causality. The transformer didn't just solve the problem of RNN, it created the foundation for the large language models and ushered in the current AI revolution. Every time you interact with a modern AI chatbot or use a high quality translation tool, you're using a system powered by the attention is all you need principle. So finally, if you found this explanation clear and helpful, please take a moment to like this video and let us know your thoughts in the comment below. What topics should we break down next? LSTMs, GRU, or maybe an even more deeper dive into the math of self-attention? Don't forget to hit that subscribe button and the notification bell so you don't miss our next deep learning breakdown here at LearningHub. Thanks for watching and keep learning.